This is part 9 of the series Logarithmic, Exponential, and Other Transcendental Functions. And in this part, we're going to investigate differentiation and integration involving exponential functions. First, we're going to have to look at what is the definition of the derivative of an exponential function. And you might be surprised by the outcome. So here we're looking at the derivative of the natural exponential function. Let u be a differentiable function of x. Therefore, the derivative with respect to x of e to the x is surprisingly e to the x. And the derivative with respect to x of e to the u, again u being a differentiable function of x, is simply e to the u du. Now, let's take a look at how this comes about. We know from one of the basic properties of logarithms that ln of e to the x is just x. Now we're going to differentiate both sides of this equation with respect to x. And so we have the derivative with respect to x of the left side equals the derivative with respect to x of the right side. The derivative of this left side is 1 over e to the x times the derivative of e to the x. And we're using the chain rule here, just like we would if we were implicitly differentiating this with respect to x. So the derivative of x we know is just 1. Now here we have 1 over e to the x times the derivative of e to the x, and we're just going to multiply both sides by e to the x. E to the x times 1 is just e to the x. So the derivative with respect to x of e to the x is e to the x. A surprising outcome. Now this idea, this property and definition of derivative of the natural exponential function, just like the derivative of natural logs, is going to be a great benefit to us when we try to integrate or differentiate some complex expressions, because we can use logarithmic and exponential differentiation coupled together to make our problems a lot easier. So let's take a look at an example how this is going to work. Here we want to differentiate e to the 2x minus 1. Now you can think of this as just an application of the chain rule where our u is 2x minus 1, and we're just going to look at this as e to the u du. So the derivative of this is just e to the 2x minus 1 times the derivative of the upper part, 2. Putting these together in a more conventional form, that's 2e to the 2x minus 1. Hopefully you find that fairly straightforward. Let's take a look at another example. Here we have another example, similar in nature. We have a differentiable function of x here as u, and this is e to the u, so our derivative is going to be e to the u du. The only difference is our du is going to be a little bit different. The derivative of this with respect to x is that original piece, e to the u, times the derivative of u. And this is the breakdown of the derivative of this guy. So this is actually negative 3 to the x minus 1. We subtract 1 from the exponent when we're differentiating and multiply by the exponent. So negative 1 times negative 1 is positive, and this is just 3x to the negative 2, and that breaks down to 3 over x squared. Then this, now convention has it that it's okay to have a natural exponential with a negative exponent in the numerator, but I just dropped them down for consistency's sake. You could leave this e to the negative 3 over x in the numerator if you wished, but I pulled it down just to be consistent here. Alright, let's take a look at another example. In this next example, we're being asked to find the point of inflection of this function. Now if you recall that a point of inflection requires us to take the second derivative, so we're going to be differentiating this guy twice. Let's go ahead and walk through this one piece at a time. The derivative of this is this whole thing times the derivative of this exponent. So the derivative of this guy, negative x squared divided by 2, is just negative x. The 2 comes out in front. We subtract 1 from the exponent. 2 divided by 2 is 1. So that's just negative x is this guy out here. We'll pull out the negative 1 here, and we have negative x times the original piece. This is the original piece here. That's our first derivative. Now for our second derivative, notice that this negative 1 over square root of 2 pi is just a constant. So we're going to pull that out to make things simpler as the constant multiple rule. So we pull that out here, and then this just becomes a product rule. X times e to the negative x squared over 2. So we don't have the negative sign anymore. That's come out here. So the derivative of this is u dv. This guy is our v, and so the derivative of that is this thing, which is just e to the negative x squared over 2 times negative x. So u dv plus v, which is the original piece here, this e to the x squared over 2, times the derivative of x, which is just 1. U dv plus v du, just 1 over here. And then to consolidate these, be careful on this part of it, because what we have is this x times this x is negative x squared, but I'm going to pull out that negative 1 out of each of these terms. So I'm going to pull out that negative 1. This negative 1 times this negative 1 becomes a positive, so there's no longer a negative sign. However, when we pull a negative 1 out of this, this becomes minus e to the negative x squared over 2. So we just change the sign of each one of these terms. This one was negative, it goes positive. This one's positive, it goes negative. And that gives us e to the x squared over 2, because again, we've pulled out this e to the negative x squared over 2 from each of these terms. So what's left on this side is just the x squared here. And when we pull an e to the negative x squared over 2 out of this term, we just have 1. So pulling out the e to the negative x squared over 2 gives us this over the square root of 2 pi times x squared minus 1. Now to find our potential points of inflection, we know that they exist when the second derivative is either 0 or undefined. Well, what we end up having, if we multiply both sides by the square root of 2 pi, that disappears, and so we just have this product. Since there's no way for this exponential to go to 0, nothing you put in here is going to drive this expression to 0. This doesn't contribute to any of our potential points of inflection. However, when we set this equal to 0, it does. You can see that if you add 1 to both sides, x squared equals 1. This is the square root of 1, which is plus or minus 1. So our potential points of inflection are negative 1 and 1. And then recalling that if the function changes concavity at each potential point of inflection, then that potential point of inflection becomes a point of inflection. So we set our test values at negative 2, 0, and 2. Could have been anything greater than 1, between negative 1 and 1, and less than 1, but these are convenient values. And if you plug this value into this, you will see it comes out positive. So this is concave up. Putting in a 0, this is concave down because it's negative. And putting in a 2 into this expression, we're concave up. And so negative 1 is the x-coordinate of our first point of inflection. When we take that negative 1 and substitute it into the original function, it gives us this. So this is our first point of inflection. And when we take this 1 and put it in to our original function, we get this point of inflection. So there's our points of inflection here. Okay, let's go ahead and look at one more example. In this problem, we're simply looking for the extrema of this function. And I think you can see at this point, we're going to take the first derivative, and this is just going to be the product rule. F prime of x is just going to be u dv. The derivative of e to the x is just e to the x plus v du. Derivative of x is just 1. Now here we can pull out an e to the x. Each one of these terms has a common e to the x term. So we pull that guy out front, and we end up having as our final form e to the x times x plus 1. And again, just like in the previous example down here, this exponential never goes to 0. There's no way to drive this to 0 because even if x is 0, e to the 0 is just 1. So this never goes to 0. And that's all we're left with is x plus 1 equals 0. Therefore, x has to be negative 1. We set up our first derivative test here with the critical number being negative 1. And our test value is negative 2 and 0. And we see that when we plug negative 2 into f prime, we get a negative, so the slope is decreasing here, and increasing when we put in a 0 for our test values. So yes, this is in fact a extreme value. It is a minimum, and when we plug that into the original function, we get negative 1 over e. So this is our minimum value at negative 1 over e. All right. Let's go ahead now and take a look at exponential integration and see how that compares with differentiation. Here, just as we did with differentiation, we're going to let u be a differentiable function of x, and the integral, or the indefinite integral antiderivative of e to the x with respect to x is just e to the x plus the constant of integration. Another really nice outcome here, just like it was for differentiation. And this follows from the fact that the derivative of e to the x is e to the x. And given that u is a differentiable function of x, the pattern we're going to try and match is e to the u du. So we're reversing the process. Before, if we took the derivative of e to the u, we would have e to the u du. Therefore, the integral of e to the u du is just e to the u plus, of course, our constant of integration. So the pattern you're going to be matching is e to the u du whenever you're dealing with the integrals of natural exponential functions. Let's go ahead and take a look at an example and see how this works. Here we have the integral of e to the 3x plus 1 dx. And so we're going to have a u du substitution thing going on here, so let's get to it. So hopefully you chose u as 3x plus 1, and therefore your du is 3x. This is naturally going to give you a du over 3 equals dx. I just combined the steps and pulled out the 1/3 because we know that this is always going to be the case, that du over 3 is going to end up being the 1/3 out front. And we have our pattern. We have the integral of e to the u du. And we know from up here, the integral of e to the u du is just e to the u plus c. We do a back substitution, substituting back our u, which is 3x plus 1, and we have 1/3 e to the 3x plus 1 plus c. Alright, I think we got time for one more example. So here we're looking for the integral of 5x e to the negative x squared. So again, we're going to set our u as negative x squared, and I think you'll see that we'll have a pattern that we can match. So if we choose u as negative x squared, du becomes negative 2x dx, so that negative 1/2 is going to come out in front, but it's also going to combine with this 5. So that 5 is coming straight out. So the constant we're going to have out here is negative 5 over 2, because this 2 drops to the denominator and it combines with this 5. And then we have again the integral of e to the u du, which is again e to the u plus c. We back substitute our u in here, and this is our final result. Alright, time is about up for this video, so we're going to continue in the next video with a few more examples. So we're not by any means done with integration of natural exponential functions. And I will talk to you in the next video.